So like I was saying, Dr. Cow is a very conceptual individual and likes to ask conceptual questions. So a lot of the information in here will be sort of mirroring that. I'm going to do my best to convey the concepts about the fundamentals of signal processing and signals in general. And very often you'll see a question that's like, it'll start with something that's sort of computational maybe, and then he'll go a little deeper and he'll ask something that's a little more fundamental. I mean, you might have seen this in the homeworks. He sort of has the same format for questions on there. And the idea is that whatever computation you did sort of at the beginning of it should lead you to some sort of fundamental answer, or sometimes it'll be a little more disjoint. It'll just be sort of like a fundamental overarching question that's sort of loosely related to what the initial question was. And oftentimes then you have to build some sort of mathematical formulation off of that fundamental intuition about the subject. So this, I'll start with just the basic stuff. Let me go ahead and share my screen. Hopefully, can you guys all see the presentation?
Yep.
Awesome. All right. So let's go ahead and get started. So first off, this entire class is about signals. It's about manipulation of signals. It's about mathematically defining signals. And this is extremely helpful, when you get into anything that has to do with electrical engineering. You want to be able to define whatever signal you're working with. And so that's sort of what this class attempts to do is give you sort of a framework for that. So you go through all these basic things: amplitude scaling, amplitude shifting, addition, multiplication, reflection. And this is sort of like a, for me at least, it was sort of like a pre-calculus review. And a lot of this stuff should look at least somewhat familiar. Maybe not so much like this time shifting, but a lot of this, it's sort of just putting names and labels on these things so that when you approach them later, you sort of know exactly what is going on, and you can sort of give it a name to all these things. And some of it's pretty relevant, like time shifting or time reversal even. So one important property of these signals is whether or not they're even or odd. And this is especially true with the Fourier transform. As you'll see, there's a lot of tricks that you can pull with even and odd signals due to the fact that a sine function is odd and a cosine function is even. And on top of that, something else that's important is the energy and power of these signals. So if something is an energy function, that means that it has essentially a finite amount of area over the x-axis over all time. And if something is a power signal, that means it's sort of, it's like a sinusoid of some sort. It continue to expand, but it sort of has like a finite amount of power that it is putting out. It has a non-increasing amount of energy over the x-axis as or the time axis as time continues on. And that's what these definitions are actually saying, right? So when you say, the integral from negative infinity to positive infinity of the magnitude of x of t squared, you're actually just saying, okay, I just want to look at what the overall volume is for this whole function, right? And then when you have something like a power function and you look at its period in particular, right? What you're looking at is you're looking at how much energy it has in a given amount of time. And you're assuming that energy is sort of continuously expanded out. Again, I reiterate these things because they become important, obviously, in later courses, but more importantly, that's sort of the intuition for why you're doing these things. And, for example, if you have a power signal, or, if you see something that's periodic or you see something that's continuing out onto infinity, it'll probably be a power signal and not an energy signal. And similarly for the opposite. Just some classic signals here. One of the most important ones that you first see in this course is the delta function, which is sort of this weird function that's defined as 0 when x is not 0, and then infinity when x is 0. And it's more importantly defined such that the integral of it, so it's the overall area that it encompasses is 1. If you think about that, it's sort of like an energy signal, sort of. But if he were to ask you a question, for example, is the delta function an energy signal? The way that you might answer that is you'll start with the definition, right? You'd say, okay, what am I going to do? I'm going to take the magnitude of a delta function and square it. And from there, you would take that integral. But the integral of delta squared is delta. So, how would you answer that? He'd probably ask a conceptual question from there about, would you consider that to be an energy function of some sort? And most importantly is the sifting property of the delta function. F of x times delta of x is f of 0, right? So essentially that, because the delta function only exists at 0, you're kind of like multiplying the f of x by a point at 0, and then it has an overall area of 1, so it's just whatever f was at 0. Yes, Natalie?
What exactly is meant by a sifting property? I always get confused with that term.
Sure, yeah. So think of it like if, imagine like the x line is like an actual like sieve, right? The delta function sort of pokes a hole in where that in the x-axis, right? And so wherever that hole is, right, that's what the value you're going to pull out. That's sort of at least conceptually the way to think about it. The reason it works like that is because the delta function is only non-zero at x equals 0, right? So if you multiply two functions together, you multiply them pointwise together. So if you multiply the delta function by some other function, then that function will then only exist at 0 then. Does that make sense?
Yeah, so essentially when you're saying you're sifting, you're just pulling out a point in time.
Yes, that's a good way to think about it. If
Okay.
Yeah.
Thank you.
Of course, yeah. And it's wherever that delta function has its 0 value inside of the term that is delta function. So if it's x minus 5, that 0 then becomes x equals 5, right? And so that's why you call it sifting, because then you can kind of choose where the holes in your sieve are, I guess. After that, you have the rectangle function. Definitely something that he likes to use a lot. And more importantly, he likes to use, I believe, this particular definition of the rectangle function, that the overall area of it is 1. You might see something like the rectangle with specifically with the delta defined, but I think he usually just uses the rectangle function defined in the second part there. And then lastly is the step function, or sometimes called the Heaviside step function, which is just, it's 0 for t less than 0 and 1 for t greater than or equal to 0. I would definitely double check your notes. I forget exactly how he defines it. It could be that he defines it as 1/2 as 0. It could be defines it that it's only for t greater than 1 and for t less than or equal to 0. That's when h of t equals 0. So double check your notes in particular on that one. But I think either way, he's going to tell you the exact definition if he were to give you a Heaviside step function, for example. An important thing to note is that the integral of the delta function is the step function. And that sort of tells you a bit of the nature of a delta function and a step function. Okay, let's go ahead and go to some pretty simple signal manipulation. This is actually from a previous midterm 1 that he put on. So go ahead and give it your best shot. Normally I would have a board to do this on. So I'll see what I can do as far as explanations go. But just go ahead and take the next like 5 or 10 minutes to try out this problem. And yeah, I will see you guys when we reconvene. So I was asked to repeat why power signals theoretically incorporate the period. So power is energy over time. So when you talk about the power of a signal, you're trying to figure out how much energy it's giving you over time, right? And the best way to do that is to ask how much energy it gives you in a certain packet of time, which is where the period comes in. You sort of, the natural definition of the packet of time that you want to look at is the period of time over which there's some sort of symmetry, right? So if you think about a sine function over its period is going to be symmetric every period, right? It's going to be the same every period. So. Okay, can I get some thumbs up reactions in the chat to see how many of you guys are good and done with this problem? Probably has been about enough time for it. You can like do you guys know how to react on Zoom? All right. Now he's doing good on this problem. I'll go ahead and say that, let me go ahead and close my window. Okay. So with this particular problem, pretty straightforward stuff. Signal manipulation, nothing meant to be too fancy. The idea is that we sort of have a triangle-like signal that we're trying to manipulate. And the real trick here is that you're sort of trying to figure out, it's that idea of stretching and shrinking something, right? So this has always been confusing to me. If you multiply something inside, aren't you stretching it? Well, not quite, you're actually shrinking it, right? For the first part, sketch the even and odd decompositions of x even of t, or even odd compositions x even of t, x odd of t. You should have gotten something that was sort of like a plateau for the even part, and something that sort of looked like a triangle sine function for the odd part. Next, sketching x of -2 plus 3 is, you should have had, what I usually do is I usually just find where it's 0, right? So sort of where does my 0 point switch to here, right? And in this case, it would switch to where t equals 3/2, right? And so I know that that's where the shift is, and then I can sort of figure out how much it stretches or shrinks from there, right? So now then I would say, okay, where would t normally be 1? Well, or in my 1 before, right, which is that whole expression is 1, right? What is it now? Where is that point now? And that would be where t, actually that would actually still be where t is 1, wouldn't it? Yeah. So you sort of get this like weird stretching phenomenon where it switches over to 3/2 and then flips, and then you sort of have this point right up here is going to still be in 1, but then you'll have a longer tail this way that's a little bit less stretched out, and a shorter tail this way that probably goes down to about 1/2. And you can apply the similar logic to this. These are just practice problems, and this is also to tell you guys, like, don't worry too much. There are questions on the midterm that are going to be, this straightforward. Okay. Any questions there? Anything anyone wants to ask about? Cool. Great. All right. Problem 2, quick true or false question. If x of t is an energy signal, then y of t equal to x of t plus 1 is also an energy signal. Who wants to be a brave person and answer this one?
I'd say it's also an energy signal. So
You'd say it's also an energy signal, so true.
Yeah.
Okay. True, question mark. All right, I'm getting a lot of trues. Well, by my tone, you can probably tell that's actually not true. Does anyone want to, so why do you think it's true? That's an important question. I'll say Tyler, I know you just answered.
This is very sad.
It's fine. Hey, you know what? There's nothing wrong with getting a question like this wrong. That's why I have them on here, right?
Well, aren't you trying to say that how I thought about it is an energy signal is finite? If it exists, it's finite. So if an energy signal exists at x of t, then I would assume it would also exist at x of t plus 1.
That's a good way to think about it. Think about this. Remember what I said about think about the mathematical definition. So whenever if you're ever unsure about something, think about the mathematical definition. The mathematical definition asks for the entire area of the signal, right? It asks for the magnitude of the signal over, all time, right? So what is the magnitude of 1? What is the area under the curve of the function y of t equals 1? So if I were to take y of t equals 1, and I were to just have that, extending out over all time, what is the area of that? Exactly. And that's the important part. So essentially, you can think of it like there is infinite energy inside of that as a result of that. Does that sort of make sense?
So if you add it by 1, it shifts up, and as a result, there's always going to be infinite energy there.
Infinite area under the curve. Infinite
area
energy.
in the curve, and that's not an energy signal then.
Exactly.
Okay.
Yeah. Does that make sense?
Yeah.
Okay, great. So this one actually is false, and the energy is not finite. So I think I have one more here. Yep. If x of t is an even signal, then y of t equal to x of t minus 1 is also an even signal. All right. Does someone else want to be brave? Let's see. You guys can also just answer in the chat. That's perfectly fine.
Wouldn't that be false unless the period is 1 itself?
Yeah, that's a good way to answer that question. That is correct. It would be false unless the period is the same, because y of minus t, and the best way to check it is just to take y of minus t, right? And that would be x of 1 minus t, or x of negative t minus 1, I should say. Yeah, and then moreover, you would say it actually would be even if the period is 1. So, or yeah. Yes, great. Okay. Oh, I forgot I had one more. Huh. Okay, if the input to an LTI system is periodic, then its output is also periodic. Okay, so this is getting a little bit into linear and time invariant systems, which I think is what I'm going to talk a little more about in the next section. But so if the input to an LTI system is periodic, then its output is also periodic. Is that true or false? Okay, I got some trues in the chat. All right. Anyone else want to answer? Margot, or Margot? Margot, I'll say Margot, is very emphatic about it being true. That's great. Love the enthusiasm. Yes, awesome. Looks like we got a lot of trues going on. No, it's perfectly fine. Don't worry. Gotta love the energy. Maybe the power. Not really sure. But you are correct. If the input to an LTI system is periodic, then its output is also periodic. And here's a quick proof as to why. But as you will learn later in the course, it is mostly because if you've taken linear algebra, the eigenfunctions of linear time invariant systems are exponentials. It's sort of a weird thing to think about. So then if you take a complex exponential, and this is sort of, for people who want to understand, who have want to understand the math a little more, if you take a complex exponential, then it's going to remain a complex exponential. So if you have, a sinusoid or a cosine, which is fundamentally just complex exponentials, then those complex exponentials will just stay the same because it's an eigenvalue. So, the actual fundamental function doesn't really change. You can also see it as if, s of x of t plus t naught is sx of t. So then then it must be true that y of t plus t naught must be y of t, which is an easier way to think about it. I'll do my best to sort of, throw a little more of this intuition in there. I know Dr. Cal really likes it, and don't worry if you don't pick up on it. Usually doesn't test on this stuff too much until later on in the course, but I think it's good to be exposed to it a little earlier. Okay. Okay. This is Yeah, we'll just keep going forward. Is the following system linear? And is it time invariant? Go ahead and think about this one for a bit. As soon as you have an answer, type it in the chat if you'd like to. I'll give you guys like, let's say, what time is it now? Let's say like 2-3 minutes. This one's not too bad. See what you can come up with. Always best to try to formulate an answer on your own. And then you guys can go ahead and start typing answers in the chat.
Isn't it both? It's definitely time invariant. Isn't it both?
That's a great question. Can you prove that it's both to me? Oh, I want to wait for everyone to
Okay.
have an idea. But if you'd like to give a reasoning, I'm more than willing to hear it out.
Well, when you do the shift input and output, they stay the same. So it's time invariant, 100%. And then system being linear is because when you do the A system and then you do the system otherwise, they stay the same.
Okay. That's good reasoning. I'll say that much. I don't want to give too much away, but I'll say that that's excellent reasoning. Let's go ahead and start talking about this guy. Okay, so we previously heard an answer from Michael. Thank you very much, Michael, about whether or not this system is linear and time invariant. Go ahead and flash the answer up here, but I can tell you it is linear but not time invariant. Very good reasoning for linear and also good ideas for time invariant, but there's something subtle here going on. And that's the side on the right that says t greater than or equal to 1. And the idea is that when you shift this in time, you don't actually shift, that doesn't change this definition of t greater than or equal to 1 here, right? And so what that sort of means is, let's say I have the signal, it sort of is cut off, x of t is cut off after a certain point, right? So it'll start like, start here and then it'll go down that way. If I shift it to the side, right? If I shift it this way, yeah, this way, I guess on the screen, doing my best to explain this. What'll happen is the function will, if it's like this sort of weird ramp signal, it will actually sort of be cut off earlier. And so you'll see a smaller ramp signal. Does that make sense?
Oh, so the problem is the 0 part on the bottom. That's what makes it time invariant, right?
It's making it not time invariant, but yes, that is correct. That's why it is a problem. Yeah, but good reasoning. The best way to go about doing that mathematically is to, like for something like this, it would be to like draw out the signal and see what it does. But the other thing to think about is just this t is greater than or equal to 1. And one of the reasons I do put this on here is because it is a bit of a tricky question. I think this was on a previous midterm, and it was one of those things that I think I got it wrong when I first looked at it. But yeah, it's important to think about that. Okay.
Sorry, can you explain one more time why it's linear?
Why it's linear? Yeah. So let's say we take, the standard check is, let's say you have two signals, AX1 plus BX2, where A and B are some numbers in the reals, right? if you go through and you look at if you were to apply this transformation to those signals, it wouldn't matter if you applied it before to the whole set of them or after to each of them. That's sort of the idea, right? And if you think about that, sort of makes sense because they're both defined, you know, it's ax1 plus bx2. If I were to have that whole system defined on it, right, I would get ax1 plus bx2 all at t minus, you know, at t minus 1 and greater, right? Or for t greater than 1. And then if I were to get, and then if I were to apply to them each individually and then multiply them by a and b and add them together, I'd get the same result.
I see.
Yeah.
Right, thank you.
Yeah. And whenever you do any linearity proof, that's what you want to prove. You want to prove that let me go ahead and see if I can, I wish I'd written this out on here. ax1 plus bx2 equals af of x1 plus bf of x2. See if you guys can see that. This is what you want to, this statement right here is what you want to prove, that f of ax1 plus bx2 is equal to af of x1 plus bf of x2. And if that's true, then your system can be considered linear. Just whenever you ask for linearity, just do that. That is, and if you want to learn more about that, take an upper division mathematics linear algebra course. It's very interesting if you ask me, but if that's sufficient for you, then, you know, power to you, maybe energy. Okay, now let's talk a little bit about probably one of the more complicated things in this class, convolution. So I'll start by saying convolution is just an operation. Don't think too much about what it means. Just sort of try to grasp what it's doing. I remember taking this class, and when I was taught convolution, I was like, what is going on here? This is the craziest thing, right? Why is this important? What does this do? But it turns out to be a very interesting operation. It's commutative, it's associative, and it's distributive with respect to addition. So it's commutative. If you have f time or convolve g, that's the same thing as having g convolve f. It's not like matrices. It doesn't matter what order you do it in. It's associative. So if you have f convolve g, convolve in a parentheses, and then convolve h, that's the same thing as having f convolve g convolve h. So again, it doesn't matter what order you even do different convolutions in. And then it's also distributive. So it's like multiplication, right? You have f convolve g plus h is the same as f convolve g plus f convolve h. And then the most important part is that x of t convolved with the delta function is x of t minus a. This is where the sifting property comes into play. So the question is, you can sort of think of the delta function as like in the same way that you have eigenvalues of matrices, the delta function is an eigenfunction of the convolution operator. It's like it's the identity of it. Nothing changes, right? If you have x of t convolved with delta of t, that's equal to x of t. And that's something that's very important because it's sort of, it is exactly the same thing as saying that that exponentials are eigenfunctions of these operators as well. So that's where that sort of idea, this is where this starts, that the delta function is a quote eigenfunction. It doesn't change something. It doesn't itself change over a convolution operation. Or convolution with a delta makes things not change, I guess is the way to say it. Okay, does that make sense to everyone? Something that's very important. Okay, great. So, impulse response. Another very important part of this class, comes up just about everywhere, is the idea of an impulse response. So if we send an impulse, a delta function, into an LTI system, it returns the quote impulse function. So the output y of t of a system with input x of t is described as that. And I wish I had the proof of that up here just so I could go through it a little more. But you can sort of think of it like if you put x of t was equal to delta of t, right? let's say you're trying to find what the, what the h of t of the system is, right? What the impulse function of the system is. If you input a delta function into the system, right? Remember, the system's operation is that it convolves whatever signal you put into it with its impulse function, right? So if you put an impulse into the system, then the impulse function is convolved with the impulse, which just means that it's convolved with the delta function, which just means it spits out itself. It spits out its own function. And that's sort of the idea of the impulse function, is that you sort of get something out of it by like poking the system. Does that make sense to everyone? Another important fact. Awesome. So due to convolution.
Sorry.
Oh, yeah.
Just quickly. So when you're saying you're convolving it with delta function, you're getting the same thing out. What is the purpose then of doing it?
When you convolve, maybe I should be a little more clear. When you convolve with a delta function in general, right? So you convolve some function with a delta function in general, you get that whatever function you convolved with the delta function out. So if I were to convolve x of t with delta of t, I would just get x of t out, right? The final result, it would be like multiplying x of t by 1 is the idea there. So when we have a system, and we know that system's operation is to convolve with some h of t, right? We know that what that system effectively does is it takes my signal and it does a convolution of some signal h of t with whatever signal I input, x of t. If we make x of t delta of t, then the overall output of the system is going to be delta t convolved with h of t. So the overall output of the system is just going to be h of t.
So essentially you're doing it to simplify other things so you can understand what's going on over there. Does that make sense?
Yep.
Okay, thank you.
Yeah. No, that's right. You are doing it so that you can simplify what's. Yeah, you're doing it to simplify it. Yeah, and to learn about the system. Yep. Okay. So due to convolution, this gives way to things like stability, step response, and oh no, blocked a little bit. Stability and step response, and then also that the system is linear. So let me see. Right. So then with the impulse response, we can essentially define stability and also like the operation of something like a step response, right? The operation of a step response is just that it like if you convolve something with u of t, it's the same thing as taking the derivative of it. Sort of a weird thing to think about. And then moreover, if a system is stable, so it always produces stable outputs, then its impulse function has a finite area. That's the idea of a stable function. Does that make sense, everyone? Okay. Okay, let's go ahead and get some questions. Another question that was on a previous midterm right here. Consider this following signal, f of t. Signal can be written as u of t minus a times rectangle of t over 2b. A is greater than 0, b is greater than 0. Find a and b. Definitely more of a sort of a weird thing to think about. You want to think about what you know here. And I'll leave you guys. I'll give you like 5-10 minutes to do this one. A little not trivial. I'll say that. All right. If you guys want, you can go and start putting just throughout the answers that you got in the chat. I see Tyler's already done that. Thanks, Tyler. I just want to see, what sort of answers everyone is getting for this. It's fine if you, want to do this problem later. I'll be sending out the slides to everyone that, oh, you know what? Before you guys leave, what I'll do is I'll get attendance of everyone through a Google form that we have that I realized I didn't send you guys before this. So make sure to stay until I get that out to you. And just in case I forget, let me know. Seeing some good answers here. Okay. All right, well, the answers are A equals 3 and B equals 1. So let's think about this a little bit. I'm going to try to reason it out verbally. Hopefully you can go back and try the problem on your own with the reasoning that I have. So first of all, we know that when we convolve the step function, with the square function, right? Or with u of t, we're essentially doing a, we're kind of integrating. Oh, hold on. Oh, that's a good question. If I remember correctly, I might be squeezing the time a little bit. I'm probably squeezing the time a little bit. This is a problem. That's very funny, Tyler. If you use that much time for this problem on it, like about 10 minutes on a problem like this, you would have time at the end to thoroughly go back through and check your answers. Like literally do every problem over again. Probably, like in the way that you do problems over again. You don't quite take the same amount of time, but you sort of like speed through it again, check your work, and recheck your reasoning, see if there was any faults with it. Oh geez, it's been 2 years, folks. So I'll do my best to answer how many questions. The question is, how many questions are there on the test? If I remember correctly, 4 to 6. And it would be like, this was like one part. It was like 4, and this was like one part of it, and there was like 2 or 3 parts for every question. I mean, you guys how long do you guys have for a test? I had 2 hours when I did it. So
same.
If you guys have 2 hours?
Yep.
Okay, so if you have roughly, I would say somewhere between 8 and 12 questions. So let's say 10 questions like this. Each of them takes you 10 minutes. That's 140 minutes, right? And some of the questions you'll breeze through, right? Some of them are those true or false ones. You'll take like 2 minutes, 3 minutes for that one. Some of them will be a little longer. But yeah, he does use the time well, I would say. For comparing the difficulty of the midterm and the homework, Dr. Cow likes to make his homework much more difficult, I would say. I would say that the midterm was easier definitively across the board. And the 2019 final had 4 questions total. I took it in 2 years ago, 2018. Okay. Yeah, no, I remember our final, he put 6 questions on there. People were like, this is way too long, which was interesting. It definitely spread out the curve a lot. To answer your question, Salvador, A, B, and C, first, like maybe 2 of them. 2018 had 6, yeah. But yeah, so it won't necessarily be like A, B, and C for all of them. Some of them it'll be like A, and A will be like something that's pretty easy, but then the B part will be like, oh, this is a hard question. And then usually if he has the A, B, and C part, it'll be like, you're just supposed to fire away at it. So. Yes, and they do have practice exams online, specifically Dr. Cow's practice exams, which is great. Okay, so I'll go back to the reasoning for this. If you take a rectangle function, right, and you sort of are doing the flip and drag technique over it, what this is sort of saying is that it takes 2 seconds, right, the amount of time that it takes to pass over the full, that it takes u of t to pass over the full rectangle function is 2, right? So we know that the length of the rectangle has to be 2. And since we already have t over 2b, and that stretches out the function, and we know the original length of the rectangle function is 1, we know we're just stretching it out by 2, which means that b has to be 1 so that the overall stretch of the function is 2. Okay? And then from there, you can, the way that I ask myself the question is I say, where do these two, where does the u of t and the rectangle function, where do they first collide? At what point do they first collide? And what this is saying is it's saying when t equals 2. So what value must a be so that these two collide initially at t equals 2? Well, we know that the rectangle starts at -1, right? So we know over here the rectangle's starting at -1. So this has to move at t equals 2. It finally reaches -1 after we flipped it over, which means that at t equals 0, right, it's 2 away from it. So if at t equals 0, it's 2 away from it after we flipped it over. If we were to flip this sort of back onto the other side, then over here, u of t is at t equals 3. That's where it starts. So a has to be 3 so that when they collide over here, u of t collides when it crosses over at that point. I know that's I wish I could draw this out more explicitly, but if you can go back and try to see that reasoning for yourself and see, oh yes, a does have to be 3 so that they collide at t equals 2, then it'll make a little more sense.
And one more thing. So it goes to amplitude 2b as they add on to each other, correct?
Yep. Yeah.
Okay, got it.
Yeah. Or 2b. It goes to amplitude 2b because when you actually, I think earlier it said convolution with u of t is like a derivative. It should be convolution with u of t is an integral. That might have been. Let me go back and see if that's a mistake in here. Give me a sec. Okay, come on. Yes. This does not look to be correct. I believe that this should say that this should be an integral. I'll get back to you guys on that one. Let me think about it a little more. But it should be that convolution with a step function is an integral, and I know that for a fact. So take that. Okay, let's go on. I think there's one more problem here. Yes. Okay, this problem. Oh boy. All right. This is not an easy problem. Oop. It says I might be cutting out a bit. Can you guys still hear me? Thumbs up from anyone? Yeah.
Yep.
Great. Awesome. Take some time to do this problem. This is one of those problems that might take you a little longer. And I would say that this is like I remember talking to my friends. I remember doing this problem, and I was like, yeah, this problem took a little longer for what it was worth. And so I know there's a little bit of drawing on here and marking. Ignore that. The question is, an input x of t is given to an LTI system with a impulse response h of t. Both x of t and h of t are shown. Let y of t denote the convolution. Find the value of t at which the output y reaches its maximum value. Determine this maximum value. Yeah, so go ahead and take some time to figure it out as you see fit. If you have like a particular question about this, PM me, or maybe you want to check your answer, and I can check you off. Feel free to message me on Zoom, and I will get back to you. Okay? I know sometimes you want to find out if your answer is right.
He has it written there. He has kind of drawn.
Hey, Nick, I got a question if you don't mind. So when you're going about doing convolution, right? So since you can do them in either order, right? Because x of t convolved with h of t is the same thing as h of t convolved. Would you say that if you need to do flip and drag, it's just better to flip and drag the simpler one? Because I would think, oh, just flip and drag x of t because it's just going to be the same thing flipped rather than doing the more complicated h of t? Or does it not really matter?
I mean, at the end of the day, it doesn't really matter. Whatever makes more sense to you, right? In this case, I would definitely also do x of t because that would make more sense to me, easier. But yeah, I don't know if there's necessarily like a right way to do that.
Yeah, well, like I know you would get the same answer either way, but it just seems easier to do the flipping and the dragging with the simpler of the two
Right.
functions, right?
Right. Yeah. Yeah, generally you want to use the simpler function to flip and drag. I mean, maybe to check your work, you do it the other way. If you have time for that. That's always a really good tactic, is to do the problem a different way and
Yeah,
try
yeah,
that
definitely.
out.
All right.
Yeah,
Thanks.
no problem. Okay, so I'll go ahead and start talking about this one, just because a lot of people have been giving answers. Good stuff. You're correct at t equals -1. I'll flash the answer on the screen actually. That's when the overlap is maximal, but the max value is actually 2. So this is where you can think about more what exactly convolution is doing. Convolution is an operation that takes the area, it multiplies these two functions onto each other and takes that area at every point, right? And sort of it's the continuous, like, okay, I'm going to look at these two functions here when they're overlapped like this, yada, yada, yada. And that t value, right, of this function, that's what convolution is. It's like how much overlap this has with this, right? So when they're sort of overlapped, you're not going to get maximum value. So as you can see, I sort of was, this triangle is actually, where this person drew this triangle is important. That's actually exactly where the maximal value is. But the idea there is that you then figure out what the area, let me first actually start with, what that would do, right? If we multiplied this x of t by h of t where it is, right? Well, that's essentially just multiplying it by 1 at that point. So if we multiply x of t minus 1 by h of t, x of t plus 1 by h of t, we would just get the triangle shifted over by 1, right? But convolution is in particular looking at the area under that triangle, right? So what is the area under that triangle? Well, it has a base of 2 and a height of 2. So 1/2 base height, it's just 2. The other way to think about that is that each of these, smaller triangles makes up half of a whole rectangle of area 2. So that's how you get that max value of 2. And the other way to think about it is that that's sort of, it sort of makes sense intuitively that when you multiply things positively together, that's where you're going to get the maximum value. And sort of anywhere else you move this triangle on here, right, it's going to have either being multiplied by 0 or being multiplied by a negative value. So that's how to intuitively do it. You can also go about actually taking the derivative of y of t and then looking at what sort of result that would get you. That would actually explicitly get you what the maximum value is through doing that. And you can look at where that, or I should say, that will give you explicitly where t equals 0, or where the maximum value is, because you can look at where the derivative is 0. Okay. Any questions about that?
I have a question, sir.
Yeah, what's up?
So in my head, as you're dragging this triangle across the initial rectangle in h of t, you're not really accounting for the tip of the triangle. So I was trying to figure out how to exclude the tip of the triangle from the convolution.
Okay. Yeah. So Okay, yeah, so you're sort of looking at like how much these areas overlap, like literally, right?
Yeah, yeah.
Okay. That is not quite what it is. The way the function is defined is that you multiply it pointwise. So you're actually really just multiplying the y values together. So at this point, I would multiply 1 by 0. And at this point, I would multiply 1 by 1/2. And then at this point, I'd multiply maybe 1/3, I don't know. Multiply 1 by 2/3, or 1, I guess technically it would have to be, right? And multiply 1 by 1 here. And then here, I would multiply 1 by what should be 2, but this is a pretty shoddy drawing. And so you're multiplying it pointwise. And then that's what the overall function is at that point. And then you look at the area under the curve there, right? So it's not an overlap function. Well, okay. It's not an overlap function like you're thinking of it. It's not like a strict and explicit overlap function. It is a multiplication function and then finding the area under it. That's a good distinction though.
Thank you. I've been thinking of that wrong this whole class. Appreciate the help. Yeah,
of course. Yeah, that's important. Remember that you're multiplying it pointwise at all of those points, which makes it really easy when the value is just 1, right? Because then you're just like, oh, if the value is 1 at everywhere where x of t exists, then you just get that function back. Okay, Natalie, you have your hand raised?
Yeah, so just to expand upon that. So how I always thought about it is like above the triangle, that's going to go to 0, right? Because the other function doesn't exist there. Is that accurate or not necessarily?
What do you mean? Like this part right here is going to go to 0?
Yeah.
Yeah, so that is not accurate. What you want to do is you want to, it's okay, don't worry. You want to multiply at every point.
So you're including that point. So you're including all the points of both of those shapes, and you're kind of trying to see where they maximal overlap as well. Is that true?
So the overall shape would not be this shape that I'm drawing out with my.
Right, that's just a visual aid.
The overall shape would just be a triangle here, is what it would be. Does that make sense why that is?
No.
Okay. That's fine.
Is it because you're looking at that you're moving the triangle, so you're just adding with the area of the triangle? The rect exists in that area, so you can add that, but the triangle doesn't exist outside of the, so you're zeroing out everything else around it, or that's also a bad way to look at it?
Might not be. Let me. That's sort of like that. Yeah. Think about it like this. When t equals -1, what I'm doing is I'm multiplying when t equals -1 and when y of t when t equals -1 and y of t, right? What I'm doing is I am multiplying x of t -1, which is where that -1 comes in, right, by h of t and finding the area under that curve. So h of t times x of t -1 is going to give me a triangle right here. Do you see why that is?
Yes.
Okay. So the operation of convolution is multiplying those functions together and changing where one of those functions is in relation to the other one. That is the operation of convolution. But at every point, you're just multiplying those functions together. And then the last step of that is to find the area under the curve. And that's sort of what your value is for the convolution, right? So if instead, for example, I had t -2, right, y of -2 would be x of t -2 times h of t. So I would get half a triangle here, right? Because it would be 1 times the right half of the triangle, and then 0 times the left half of the triangle, and then find the area under that. And that area would probably be 1. Does that make sense?
A little. I think I'm a visual person, so I might try draw this out myself later. So if anyone else, so I don't hold everyone else up with
yeah. No worries. It's good. It's good to be thinking through all this stuff. This is definitely if you can get past this concept, Fourier analysis is just math, and this is really where the meat of this subject is. So
I guess you shouldn't think of it like you're thinking of a delta function, which is what I'm doing. You should be thinking of it as you're adding all the points that exist, right? Is that like a flip, or is that also just inaccurate and I should go draw it?
You're multiplying all the points that exist, not adding. But yes. Does that make sense?
Okay, because so if your triangle is 0, often let's say like at a half, right?
Yeah.
Then your convolution 0.
If your triangle is 0 after a half, then your convolution.
If it doesn't exist, then either your point on the triangle is going to be 0 for that point, so it doesn't exist. Outside the triangle, there is no function because it's only where they both overlap that you're getting a function. So at the tip of the triangle, it's going to expand because you have the whole area of overlap below that little tip.
No, you definitely go back and look at this again. How about this? I'm going to stay on after the review session because sorry for being late and everything like that. And we can go more into detail about it, and I'll help you. Okay.
Thank you.
Yeah, no problem. Okay. Okay, let me just go through and answer some questions here. You can think of it as multiplying the value of both the triangle and rectangle at the maximum time t equals -1. So the max value of the triangle is 2 and the max value of the rectangle is 1. No. You take the area. What you're doing is remember that what the ultimate operation is that integral. So you're taking the area of it. And the area under the triangle is 2 overall, right? And you're multiplying the triangle at all these points by 1. Was this a part of your homework? I'll go more into detail about that. I think that was a bit of a rough explanation, but I'll go into detail about that. So was this a part of your homework? This was, I believe, on one of my tests. But if you put it on a homework, that means that one of the problems that was on my homework is probably on your guys' test. I will be posting this on our HKN YouTube. So, if you want to go back through and look at these slides, I'll also send, like I said, I'll send out the slides to you guys. Last question. So in between the points -2 to 0 in the h of t, when the triangle is there, what is the equation for the x of t minus tau? That is a good question. So in the point where y is a maximum, x of t tau is equal to 1. So x of t minus tau is 1. Let's see if I got that right. X of t minus tau is the triangle function at -1. Yes. So what that does when you in the ultimate operation of convolution, what that does is the ultimate operation of convolution, remember, is multiplying those two functions together and then taking the area, right? So again, when x of t minus 1, or t plus 1, I should say, when t plus 1 appears here, right? Or when this triangle appears here, what's gonna happen is h of t and x of t plus 1 are gonna multiply, right? Pointwise. And what'll happen is you're multiplying, essentially what you're doing is you're multiplying x of t plus 1 by 1, right? You're multiplying it by just 1 here. Over this whole section, it's just 1. So what that ends up doing is you just get your regular triangle function back out, right? Because you're just multiplying it by 1. Imagine if h of t was just 1 in general. Like it wasn't this weird complex function, it was just 1. Then no matter where you convolve it, you're just going to get, the triangle function back out of it, right? So if you were to convolve h of t with 1, you just get, you just get it back out. Well, that's not true because you get it. But if you were to multiply h of t by x of t, then you just get x of t back out, right? That makes sense. So it's sort of what you're doing here is you're just multiplying x of t by 1 because it's just 1 for every value that x of t is non-zero here. So then convolution then takes the area of that. And the area of that is the area of this triangle, which is 2. Any questions there? I just lost a bit of light. Give me 1 second. Let me see if I can get some more. Okay. So, like I said, convolution is probably one of the most confusing parts about this class, if not the most confusing. I personally found it to be the most confusing. And it's a weird operation, but it's just that. It's just an operation. Okay, let's keep going forward. All right, Fourier series. Okay, so I don't have any, I'll preface this by saying I don't have any particular problems set up for Fourier series, but I will go through a quick review of this. I also noticed it's 5:20 and I want to save a good amount of time for your guys' questions, alleviating concerns, things like that. And if you guys have particular questions with Fourier series, I can answer those. And more importantly, I will I can maybe try to scrounge up a problem. I thought there was one in this slide deck, but there isn't. But I know I have one somewhere, so I can pull one. So let's go ahead and get started. The fundamental idea of the Fourier series is that I can build a function out of sines and cosines. That is the idea. If you take a vector, any vector, this is sort of unrelated. Think of a vector in the Cartesian plane. And let's say I have a set of other vectors and I want to build my original vector out of those other vectors. I have a vector A and I have a vector, B1, B2, B3 onto infinity. I only need two vectors to do that, right? I only need B1 and B2 as long as B1 and B2 are, B1 dotted, or B1 is not some scalar multiple of B2. But more importantly, if I were to take all of those vectors, right, as long as one of them isn't a scalar multiple of the other one, right, I could somehow, awkwardly form let's say a vector like up here, and I have like all these like weird smaller vectors, and they like go in this direction, all these weird ways. I could probably find a way to multiply, add them all together, so eventually I get back to this vector, and then the overall formation is just this vector right here. And I'll say that that's essentially what you're doing with Fourier series. The issue is that is that technically, it's in like a higher dimensional space, but the idea is that you sort of have all these like building blocks for functions, and your building blocks are just exponentials, right? Or sorry, sinusoids. And so by using all these sinusoids, you can sort of slowly build up your function. I'm sure he showed you guys like a square function, right? And sort of you start with just a regular sinusoid, not a very good approximation. And then you take a different sinusoid, and it sort of gets to be a slightly better approximation. It looks something like, right? And then you get better and better and better until eventually, the line at the top starts to look really flat, and then it goes back down and it starts to look a little bit like a square function. And that's the idea. So going a little more into the math, what is more important is that over a period of a sine or cosine, over a period of sine or cosine, if you multiply a cosine by a cosine of the same period, the overall integral will give you something. But if you multiply a cosine by a sine, you'll get 0. So it's like taking a dot product of vectors when those vectors are orthogonal. You get 0. In fact, that is technically exactly what you're doing. And that is very useful. That is like the fundamental useful part of using sines and cosines, is that sines and cosines are orthogonal. Moreover, sines and cosines of different cosines are of different a cosine of one frequency is orthogonal to a cosine of another frequency. So this all sounds like a lot of jargon and mess, but what that really means is that if I take this integral right here, I just extract those values, the weights of each of these cosines of different frequencies, which is what this operation right here is doing. Let me see if I can. So this mathematically is how you extract those weights. Your a sub n that you multiply by each cosine of each frequency, and this is how you extract the b sub n. So you multiply the sine of each frequency, and then this is what your overall sum would be, and what your overall function would be. And these are just some quick functions. If you want to actually specifically look at the amplitude phase spectra, you can use something like this. And moreover, that a sub n is actually defined to be an squared plus bn squared, and that psi sub n is defined to be arctan of bn comma an. So it's sort of like, you have like orthogonal vectors in your vector space, right? Your finding the overall amplitude by summing the sides of the triangle, right? Or by taking the Pythagorean theorem for the sides of the triangle. And then you're finding the angle between them through taking the tangent of, or the inverse tangent of those. Okay. Oh, here we go. Yeah, I'll get to some tricks. Okay, that if you plug through the math and you chug through the math and you do a lot of the math, it'll make much more sense. The best way to learn Fourier series is to just go through problems and just try to find the Fourier series of functions. Good functions to use are square waves, sinc waves. Oh, sorry, I guess really any periodic function, like a ramp signal, like a triangle signal maybe. All of them good. Just if you're worried about it, just go through and take functions of that, and then you can plug it into Wolfram alpha. You can probably look up a forum online. What's the Fourier series of a triangle function, right? Someone will have figured it out and they'll tell you, or you can use Wolfram alpha to figure it out. But what's even more important than doing that is understanding these properties. He asks, Dr. Cow asks about these properties all the time, and knowing these properties is important, and knowing why these properties are the way they are is important as well. So first of all, anything that can be described by linearity in general, right? You're linearly adding these signals together, and so linearity is sort of like a fundamental property of the Fourier series, right? So like if you were to take the Fourier series of something and take the Fourier series of another thing and then smash those two together, that'd be the same thing as taking the Fourier series of those two functions originally smushed together. On top of that, there are these symmetries in the Fourier series. So when x of t is a real function, that means that c of negative k, so c for all let me go back here. Oh my, sometimes this doesn't work. Okay. When n is negative, right? And when n is positive. Actually, really quickly, do you guys use complex numbers? I should have asked that to start with. Do you guys use complex numbers?
Yeah, like complex exponentials and
yes.
Euler. Yeah, we use that.
Oh, okay, good. that would have been a bit dangerous if not. But the point of this is that for your coefficient, in that case I shouldn't have used sines and cosines. I should have used exponentials. So I'll just go back really quickly to, oh, come on. There we go. Oh, my computer just doesn't respond. If I go back to this, the other way you can describe this is with exponentials, just a sum of an exponential of a certain frequency, and that frequency increasing by integer amounts. So this is a sort of a sine cosine form, but I should have put the actual exponential form up here. But if you use exponentials, you'll have, what you'll see is that if x of t is a real function, then c of negative k, so that is to say where all the frequencies are negative, right? So that the coefficients where all the frequencies are negative is the same as c of k star. So what that means is that it's equal to the same as if you take the complex conjugate of the real coefficients. C, and then if it's even, then you can actually simplify this even more to say that not just if it's complex conjugate, but actually they are the same. So you'll sort of have like a symmetric Fourier series. So like c of -1 will be the same as c1, right? So when let's say I have e to the negative I 2 pi omega, or e to the negative I omega k t, then the coefficient for e to the I omega kt will be the same as the coefficient for e to the minus I omega kt when it's even. And then when it's odd, you'll get that the coefficient for e to the minus I omega kt is the same as the negative coefficient of e to the I omega kt. That was probably a mouthful. This comes directly out of how even and odd functions interact with sines and cosines, and the fact that even functions are cosines and odd functions are sines. you can think of it, sorry, yeah, even functions are cosines, odd functions are sines, I was right. You can think of it that when you have an even function, you have that, you know, if you only had cosines, right? And if you have an even function, then whatever your function is only built out of cosines. Your coefficients have to be the same because they're all going to be the coefficients of the cosines. And a cosine is e to the I omega t plus e to the minus I omega t. So the coefficient of e to the I omega t and e to the minus I omega of t are the same because it's the coefficient of the cosine that they make up. And then sort of the inverse is true for the sine, right? That because you switch that plus sign to a minus sign with a sine wave, then your C of k will then negatively reflect over that. I'll go ahead and keep going. If that was confusing, I can explain more later. I want to make sure that I don't run too far over. Okay, what's 5:30? So for time shifting, you have this simple multiplication by a constant factor, specifically being e to the minus I 2 pi k t naught over t. For time reversal, you just have that the coefficients become the negative of k, which sort of makes sense, right? It's sort of like you switch this negative sign over to the k. And then for time scaling, you do the same thing, right? You sort of switch the a over to the k, and that sort of increases all your frequencies because, and hopefully that makes sense, that as you squeeze your function, because you're scaling, you do this time scaling, right? As if a were to be increasing, let's say, right? As you, if a was greater than 1, you squeeze your function together. And as you squeeze your function together, you have to use higher frequency components to accurately represent that, right? In order to get those features, those features that are close together in time, you can't use sines and cosines that have very long periods. You can't use things that are, very drawn out. You have to use things that are very close together in order to figure that out, in order to properly represent that. Right, so the idea is that the harmonics change, but then the actual coefficients would remain the same. So, the actual like coefficients of each exponential, the weights of each exponential would stay the same, but the harmonics would change. But the frequencies would change. Okay, let's see. I think after that, and then the tricks. Okay, so orthogonality. This is something I mentioned before. The integral of sine of n of x times sine of m of x over their period is 0 if m is not equal to n. It's equal to pi otherwise, and it's the same for cosine. And if you multiply sine of nx plus cosine of mx for any n and m, it's equal to 0 as well. That orthogonality is important. And again, if it's even, you only have cosines. If it's odd, you only have sines. And then if it's neither even nor odd, then you actually have both. And you could actually do a decomposition of it into even and odd parts, in which case you would get cosines and sines. Okay. I don't think I have a question for you guys about that. I'm going to go ahead and stop sharing my screen. From here, I will stop the recording. So if you're watching this later, good luck. And I